Okay, magnetic field, which I hesitated just then because I told you I wasn't going to talk about magnetic field, but then here we are. So sometimes things just happen. All right, magnetic fields, or any other type of field for that matter, can be represented by field lines in the same way that we represent electric fields. But magnetic field lines go from north to south, right? So from north, which is just what we call a magnetic pole, and south, which is the opposite magnetic pole. But I want to caution you to be careful thinking about magnetic field lines and the force that a charge moving in the field would experience. Because remember, for an electric field, a positive charge would experience a force along the direction of the electric field lines. I kind of described it as like if you drop a charge in the river, if it's a positive charge, it's going to go along the lines of the electric field, or if it's a negative charge, it'll go directly reverse of what the electric field lines show, right? And so the electric field lines give some indication of what the current will be, right? This isn't so for magnetic fields. Magnetic field, positive charge, does not experience a force in the same direction as the magnetic field. And that shows up, it's just the force is along the same direction as the E vector, the electric field vector. But here we have this pesky cross product, and so you have this orthogonalness, right? So if you have a B field one way, then you're going to have the force be another way, right? So the magnetic field lines do not tell you quickly and visually where a positive charge would begin traveling when subjected to this magnetic force. It's orthogonal to that. So instead, and we just talked about this a little bit, the direction of force is given by the right-hand rule to be along the axis orthogonal to both the velocity and the magnetic field vectors. It's the same way as how torque worked. And we just introduced our 3D vectors a little bit early. And the next thing to talk about would be magnetic flux, right? We talked about electric flux as being the amount of electric field lines that are going through some, right, area, right? Remember that? And we had this quantity, which was phi sub E. So this is flux, and this tells you that it's electric flux, right? And that was Gauss's law, so it's Q over epsilon naught, right? That kind of thing. Well, now we're going to talk about magnetic flux, because magnetic fields exist and magnetic field lines exist, and so there's probably, you might guess, something interesting about if magnetic field lines happen to go through some area, just like with electric. And you wouldn't be wrong. So magnetic flux works just the same as electric flux, except the results in the end are different, which we're going to talk about. And of course, we denote it not with a sub E, we denote it with a sub B. So magnetic flux gets the same symbol, because that's the symbol for flux in general. But magnetic flux, magnetic flux, right, since that's what we're talking about, is denoted with a subscript of B. And we can reason our way to a completely different conclusion about magnetic flux through a closed surface, Gaussian surface, right, than we did with electric. So let's do that. So it starts with knowing that unlike for charge, there are no magnetic monopoles. What is a monopole? A monopole is a single individual magnetic north or magnetic south. So a monopole for the electric, in the electric world, would be a single positive charge, right, plus Q, or a single negative charge. And the electric field would go from positive to negative, and we've seen what these look like. This would be like a dipole, and this would be the electric field, right? And so the electric field starts at the positive charge, and it ends at the negative charge. This is a monopole because it can exist on its own. It doesn't need its corollary negative charge to exist. You can just have a positive charge on its own. And a magnetic field can exist around it, no problemo. You can have a monopole of charge. You cannot have a magnetic monopole. There's no such thing. There is no analog. So you cannot have, in other words, just some north part of a magnet, and therefore, some electric field or some magnetic field going away from north, right? Right, it would look like this. You cannot have this. You cannot have that. You have to have a north paired with a south. Right? And then the magnetic field lines go from north to south, but they don't stop. They continue on, right? And they're just big loops like this. All right, I'll do one more because then it'll be symmetric. That was fun. They have to be big loops like this, so there's no magnetic monopoles. So therefore, let's go back to thinking about our Gaussian surface, right? What did we do when we were talking about Gauss's law and the Gaussian surface and all this stuff that I promised you would be useful, even though it seemed like just a duplication of the same logic. So we took, some charge, we'll just say it's some positive unit charge or something, and then we took and applied a imaginary surface, right? We consider it a sphere, but it can be any arbitrary imaginary surface around it. And then we thought about the electric field that was the flux of the electric field, the electric flux through that Gaussian surface. Yeah? So electric field, right? And we related the total flux to the total charge that was inside. But we also talked about the fact that there are situations where there could be no net flux, right? So if you have a positive charge and you have an equal negative charge inside your Gaussian surface, right? This is your surface. So of course we have electric field lines going like this, right? And then they get wider and wider, right? And so you can go out to infinity with this. And so for every bit, like, brand new color, every bit like right here and right here and right here, this is flux, right? These lines are representing flux. And for every amount that is going out over on this side, there's an equal amount of inward electric flux. And so the net flux, so the net electric flux in this case would be 0. You would have to have some uneven distribution of positive and negative charge for there to be some net flux, right? So in the magnetic scene, if you have to have for every north a paired south, right? For every north, you have to have a south, then there cannot be any net flux. There cannot be. So if we did a Gaussian surface is a concept that applies just as much to magnetic as it does to electric, because it's just an imaginary enclosed surface around the thing, yeah? So if we did a surface around this thing, and we considered the net flux, well, there's an equal amount north and south, and so it's the same thing over here. If I were to draw, right, if we were to continue all of this to the outer bits, and we continue analyzing every bit that goes out and in, right, you'd have the same situation where they all cancel out. The net inward and outward flux is equal, or 0. The net flux is 0. So the net flux, net magnetic flux, in all cases, in every case, because it by definition, it has to be paired north and south. And so in in every case, the net magnetic flux has to be 0, right? So let's see. Let's pick back up with my notes here. So yeah, there are always loops, blah, 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 blah. I guess that's all I wanted to say, but I will say verbally that magnetic norths and souths bar magnets, if it, that might kind of like feel weird. So if you have a bar magnet, and you might be inclined to think, well, gosh, I know bar magnets have norths and souths, right? This is the south end, and this is the north end. I mean, what if I just, took a saw and cut right through and separated these two pieces? Well, then you would think that you would have a full north and a full south. But instead, you have created 2 new bar magnets. And you have north here, and you have a south here, right? And so it's always just one pole is relative to the other. It's nothing on its own. It's not a thing on its own. It always has to have its buddy. So that's kind of how I thought earthworms worked when I was a kid. And so I'm sorry to say that I went around chopping earthworms one day. And then I found out much later that my benevolence of gifting the world duplicate earthworms actually was just senseless horror. But there is a worm that works that way. It's called a planarian flatworm, and you should Google it. It's like made of stem cells or something, I guess. And so it can regenerate like a whole new face very quickly if you chop it in any different way. And it's very fascinating. So Google planarian earthworm. And that's kind of, you can think of how bar magnets work or magnetic things work.